Hello, today we'll look into a resistor capacitor circuit. And this type of circuits are used so often, we don't call it a resistor capacitor circuit, but an RC circuit, where R stands for resistor and C stands for capacitor. We will look at how the voltages over these components changes over time, and since the capacitor voltage is more important, we will call this voltage V out. So before we close the switch, we will look at what happens before the switch is closed, so before T is 0. Well, if we assume that the capacitor is initially uncharged, so there's no charge on the capacitor, no charge can flow into the capacitor since the switch is closed, and this means that Q is equal to 0. According to the charge-voltage relationship of a capacitor, this means that V out is also 0 if T is smaller than 0. This is of course only true if the capacitor is indeed not charged in the beginning. There are many situations where there is charge in the beginning, but for now there's no charge, so V out is equal to 0. Now we'll look what happens when the switch is closed. Now current can flow into the resistor and into the capacitor, and we call this current I. We know, according to the Kirchhoff voltage law, that the voltage over the resistor plus the voltage over the capacitor should be equal to 5 volts. And we know that the voltage over the resistor is the current times the resistance, which is I times R. We can fill this into our equation to obtain that I times R plus V out is equal to 5, and we can rewrite this as V out is equal to 5 minus I times R. Since the resistor and capacitors are in series connected, all the current flows into the resistor, flows also into the capacitor, and according to the lecture, the current and the voltage of the capacitor have the following relationship. The current is the capacitance times the derivative of V out, and we can fill this in for I to obtain that V out is equal to 5 minus C times the derivative of V out times R. We can now rewrite this equation to obtain that R times C times the derivative of V out is equal to 5 minus V out. And if we divide both sides by RC, we can obtain that the derivative of V out is 1 over RC times 5 minus V out. This type of equation is called a differential equation, and this may look difficult or scary, but do not worry, we will deal with it step by step. So we are looking for an equation which derivative is still partly itself. What type of function has this property? Well, we know that V out could be a polynomial, where V out is C times T to the power n, where n is just any number. V out can be a sinusoidal function, and V out could be an exponent function. We can take the derivative of each function and see for which derivative it still contains itself somehow. For the polynomial, the derivative is n times c times the t to the power n minus 1. The polynomial is now 1 power less than the original polynomial and thus not equal to itself, and therefore we cannot use this. If we differentiate the sine function, we get a cosine function. This is similar but not the same, so we can also not use this equation. Finally, if we differentiate the exponent function, we obtain that the derivative of V out is a times c times e to the power ct. This is equal to itself. Of course, the amplitudes are different, but we can work with this, so this is fine. So therefore, we will continue with the exponent function. So V out is equal to a times e to the power ct. If we differentiate it, we get that the derivative of V out is a times c times e to the power ct. And if we look at our differential equation, we see there is a coefficient before V out, and this coefficient is minus 1 over Rc. This means that C is equal to minus 1 over Rc. If you fill this into our equation for V out, we obtain that V out is a times e to the power minus 1 over Rc times t. We can now rewrite the differential equation and fill in what we have so far. The derivative of V out is minus 1 over Rc times a times e to the power minus 1 over Rc times t. If we fill in V out, we obtain that the right hand side is 1 over Rc times 5 minus 8 times e to the power minus 1 over Rc times t. But hang on, these sides are not equal to each other. There's a 5 and not on the left hand side, so these sides are not equal. Well, we can get rid of this 5 by adding 5 to our output equation. And if we differentiate it, it would still be the same because the derivative of a constant is 0. If we now add 5 on the bottom, we can cancel out those 5's, and we get an equation that is equal on both sides. If we work out the brackets, we can see that both sides are equal to minus 1 over RC times A times e to the power minus 1 over RC times t. So we have that V out is equal to A times e to the power minus 1 over RC times t plus 5, and this satisfies our differential equation. But what about the A? Can we just use it, or is it something specific? Remember that in the beginning we said that the voltage at t equals 0 is 0. Therefore, if we fill in t is 0 into our equation, we obtain that this is A times e to the power 0 plus 5, and e to the power 0 is 1, so we obtain A plus 5. This should be equal to 0, so we get that A plus 5 is 0, and therefore A is equal to minus 5. So then we get that V out is equal to minus 5 times e to the power minus 1 over RC times t plus 5, and this is our final equation. If we plot it against time, we can see it starts at 0 as we expected, and then it goes up to 5, and it will stay there. This was this work example. Thank you for watching, and good luck with your exercises.